I'd like to introduce myself. My name is Kyle Collins. I'm the Interim Director of the Eagle Flight Research Center at Embry-Riddle Aeronautical University. And today this presentation is going to be on the urban air mobility research activities that we have going on within our center. So in short, our mission is to advance manned and unmanned flight through the fusion of both theoretical and hardware-based research related to alternative propulsion, flight control, autonomy, and the development of novel aircraft. So some of the different elements on which we work are electric aircraft, advanced air mobility, eVTOL, hybrid electric power systems for aircraft, simplified vehicle operations. This is the idea of making the aircraft easier to fly, easier to learn how to fly. Rotorcraft, aeromechanics, rotor propeller acoustics, flight dynamics and control, and the certification of these types of aircraft. A little bit about the organization. The Eagle Flight Research Center is underneath the College of Engineering, so I report to our dean, Dr. Jim Gregory. We have a few staff. A couple of those are here, of Jonathan and Patrick. Jonathan is our shop manager. He's an A&P IA, and then Patrick Hrzwicki, an Embry-Riddle Aerospace engineering graduate, is our engineering project manager. And the previous director of the lab, Dr. Pat Anderson, also helps us on a variety of different projects. So we also collaborate with a lot of different professors across campus. We have open arms to them. It's a force multiplier for us, so we have skill sets in helicopter aerodynamics. We have Dr. Gordon Leishman, a distinguished professor, dynamics and control professors, computational fluid dynamics, structures, power electronics, and also human factors. So for our students, and maybe there's some students in the audience that want to get involved at the Eagle Flight Research Center, we also have an open door. You can come, and we have a whole volunteer track that can potentially lead to a paid position, and then we have a lot of students that come in, start that way, and then they wind up going to grad school and having some of their graduate studies paid for by working on projects that are sponsored. Here's just a short list of some of the funded research we've had over the years. In 2019, Boeing sponsored us to build a hybrid electric test bed. It was about 100 kilowatts. I'll talk about that. We've on 2 years now with the FAA that's looking at integrated propulsion and control for rotorcraft. This is specifically aimed at eVTOLs and urban air mobility. We also had a company that sponsored us to do some simplified vehicle operation studies where we partnered with our human factors department. We did human test trials. We have another STTR, STTR, with a company called Wayfarer. We're looking at integrated propulsion, high lift propulsors. These are like putting propellers on the front of a wing. I'll talk about that. And then most recently, we've had a company that makes a manned/unmanned multi-copter come to us with a desire to improve the performance of their rotor system. So they've sent us one of their rotors. We are currently testing that. And we're also doing a lot of analytical studies to do optimization and improve upon the design. So I'll start out with talking about one of our projects that's not funded by an external sponsor. This is internally funded. It's called eSpirit of St. Louis, and it's electric aircraft. We took a Diamond HK-36 motor glider. We pulled the gas engine off of that, and we replaced it with a YASA electric motor, an inverter. We're building the batteries for this aircraft in-house. And this project is great. A lot of our students are really interested in it because they get to cut their teeth on electric aviation. So in the classroom, they might not learn what an inverter is, but when they come to our lab, they actually not only learn what it is, but they learn how to program it. And we met a milestone here. Again, I said we developed our own batteries, and we've taxied it around under its own power. And we're in our current phase. We have students and professors that are helping us develop the next generation of battery packs for our future flight tests. So this is the STTR NASA that NASA STTR that we're working on for a company that's called Wayfarer Aircraft R&D. And Wayfarer has a patented integrated propulsive lift device. You can see in the lower right-hand corner where there's propellers across the front of what is essentially our Cessna 182 flight test vehicle. So the first phase was just to go through a lot of design iterations and analytical studies to see how much the lift would be improved with these props on the front, blowing air. There's also a slat. We're right now writing the proposal for phase 2, where we're probably going to build a 1/3 scale model of this with propellers on the front and do system identification. So now I'll just kind of shift gears a little bit and talk about some of our hybrid electric propulsion efforts. The first I'll talk about is our Boeing codename Phoenix system. It's a 120 kilowatt. And this picture here on the right-hand side shows you what our test bed looks like. There's in that cage, there's a Rotax 915 IS. It's a 140 horsepower, 4-cylinder gas engine. It's coupled directly to a YASA electric motor that was a custom wound motor for us. It's being run in regenerative mode, obviously. There's an inverter that takes the 3-phase AC from the motor and converts that into DC. There's also a battery pack we developed in-house. I'll be showing you some pictures of that later. It's a 450 volt lithium ion immersion cooled battery pack. And then we have this control panel here that gives us all sorts of feedback on temperatures and power levels. On the left-hand side, this is a really fascinating device. It's a programmable electric load. So we can feed it some sort of time history of kilowatts versus time. We can also just request a straight up, pull 50 kilowatts from the system. We could hook it up to a battery, pull energy from the battery. So it's a great test instrument for us. But the fact that we can give it a time history allows us to do something really neat. We can take a Simulink or a mathematical model of the aircraft that this would be on, and we can simulate that aircraft through varying levels of turbulence. We can replay that power versus time profile on our active loads, and then we can see how well the hybrid electric system actually responds to that. Here's just a little bit on the specs. The system actually, while it produces 88 kilowatts continuously, that's what the gas engine coupled to the motor or the generator can provide. It actually can do a peak output of 120 kilowatts. It does this by pulling energy from the battery that's hooked to it. So you design the battery in such a way that it can provide the power levels you need for, say, a hover or takeoff for a number of minutes, and then while it's in cruise, the battery can be recharged to a significant level so that you can land in the same manner where you're pulling some energy from the battery. Our specific energy, 460 watt hours per kilogram with only 8 gallons of gas on board, so it's a significant step up from current battery technology. The other hybrid electric propulsion system that we're working, we leveraged a lot of what we learned on the Phoenix system for Boeing, and combined with the state of Florida, which provided us some grants to purchase some equipment, we now are building a 100 kilowatt peak system that's called codename Voltron. We called it Voltron because we were pulling volts from a gas engine that's called a Rotorcraft. It's a rotary engine. If you're familiar with the Mazda that used Wankel engines, it's the same concept. This is a twin rotary. Those engines have a very high power to weight ratio, so we're expecting to have the whole system to have a higher power to weight ratio as well. So this is just a picture of the students that are involved. One of our students that's poured his heart and soul into this, he can't graduate until he finishes it. So he's working day and night to try to get this thing running. And he's, anytime you deal with hardware, I don't think people really understand that it's difficult trying to get all the pieces to talk to one another and get them programmed correctly. And you run into roadblocks almost every step of the way. So it's another great learning experience for our students to persevere and battle through those, figure out how to make it work, and keep pressing on. This is what the system looked like. It has a similar little stand that we're going to sit it on, but it's a much smaller form factor. Its peak is going to be 100 kilowatts. It's 20 kilowatts less, but the engine is not as powerful. It's only got a continuous generation of 52 kilowatts. Sorry about that. But if you notice, the specific energy is 610 watt hours per kilogram, which is higher than what we'll see on our Phoenix system. And we're planning on using the same battery for this system as well. Okay. So in-house, the same technology and systems that we use to develop the battery, the 450 volt lithium ion immersion cooled battery that you'll see some pictures of in a moment, we've developed a lot of different in-house capabilities to build the packs. So it's pretty easy now to generate. There's companies that provide, you can do your printed circuit board design and get the circuit board sent back to you relatively quickly. It's a lot like rapid prototyping of printed circuit boards. So our students who interface with our electrical engineering computer science professors, they will develop the printed circuit boards, which you can see as in the red on this. All the blue cylindrical cells are our 18650 battery cells. Those are lithium ion cells. The green board on top is part of the battery management system. So what you see on the left is a pack module. It might have a voltage of around 45 to 50 volts. Then we can combine all of those modules together to get to the voltage that we need. And you can see all of the copper bus bars, and then what you can't really see is that it's immersed in a fluid that's called OptiCool. It's a dielectric, so we can pour it directly on the electronics. It doesn't affect them in any way, but it kind of acts like a heat sink. So it's still somewhat passively cooled. I guess if you can also circulate that type of fluid through a radiator if you want active cooling, but that does add weight. So we designed this so that we wouldn't have to do that. But the liquid itself does add weight to the pack. And there's our previous director, Dr. Pat Anderson, showing us what our CNC Bond Machine looks like. We have, I think this shows how that works. So once we design our pack, we can actually program in how we want the cells connected to the printed circuit board, and this piece of equipment will go in and put those physical bonds on in a computer-driven manner. And this is what those bonds look like after they're finished. Okay. Another project that we have going on right now in the center is a rotor analysis, test, and optimization. We have a company that sent us some of their equipment to test, and we're using that to not only test, but then the data that we're generating, we can validate the theoretical models that we're building in software that we have. And then once we do that validation, we can then use the software to try to find an optimum. And then we can go back out to the test and test that maybe optimum pitch settings, or we can also test, at some point the plan is to actually have a new set of blades built, and then we'll test those blades. So the picture on the right is a little snippet from our analytical models. You can see in this scenario, it's a 3-bladed coaxial counter. Can't really tell that it's counter-rotating. You have to get up close to see, but it is. And then just a little bit of the process. For a lot of our projects, we really try to put together what's the methodology that we're following. And so in this case, we're testing their equipment, we're validating our models, then we're doing some design space exploration to find the best designs. And then at some point we'll try to verify those with spot checks with computational fluid dynamics before purchasing the build of a new set of blades to test. For higher fidelity analysis, we have the capability in-house to couple our computational structural dynamics code that's called RCAS. It's an Army code. It stands for Rotorcraft Comprehensive Analysis System. We can couple that with one of the professors in our AE department runs Star CCM, which is a CFD tool, and we work together to couple those. Then we can take that analysis, we get a lot of performance data, but we can also get blade surface pressures that can be fed into a code that was developed at Penn State University called WAP-WAP, which can calculate the noise that rotor system, it's actually generic. You could have, as long as you have surface pressures on anything, it could be landing gear, it could be an aircraft, it will propagate that to different observer locations. All right, a little bit about our simplified vehicle operations research and how we did a urban air mobility inceptor concept evaluation. So for this project, it was a very short project. We had to pull all hands on deck. The company wanted us to build a simulator that had motion. So we built we actually purchased an off-the-shelf seat that has 2 degrees of freedom at pitch and roll. We bought monitors that we could wrap around the seat, and then the idea is that this system can have custom flight dynamics. We've built all of our own models of the electric vertical takeoff and landing. It was a lift plus cruise model. It had an interface with MATLAB and Simulink, so we could have the model run in that particular mathematical software and then project on the screen what the pilot would be seeing outside. And then most importantly, we had to be able to reconfigure the inceptors so that we could test different types. And we have a 2 degree of freedom motion, so 180-degree field of view. And so we used Microsoft Flight Simulator. We went through several different iterations. We tried Microsoft Flight Simulator. We tried X-Plane. We also tried an open source flight gear. We got all of them to work, but we kind of stuck with Microsoft because it had really good graphics. And then we were able to actually build custom scenery inside the simulator. So we could build tests that the user could do. In this image, you see a highway in the sky test where we did an approach to landing. And then we did a lot of logging of the data and post-processing so that our team of human factors experts could analyze how well the pilot was doing. So we had pilots that were 0 experience all the way up through very experienced tilt rotor pilots and everywhere in between. So we wanted to know not only what their opinions were, but we also wanted to know how well they were doing when we looked at the data. So how well did you stay on track? And then, as you might imagine, this was a human subject trial, so we had to partner with our human factors professors in the College of Arts and Sciences, and it was a really great teamwork, and we did a really good job on this. I'm really proud of my team on that. Just another view of some of the different handling qualities test elements that we developed in Microsoft Flight Simulator. So look at just some of the logging that took place. This was instantaneous. As soon as the person was off the simulator, we had all of this data. This is a video of, that was a pirouette maneuver. This would be a slalom course, and here he's just flying around. So it was really, the aircraft, the simulator was quite easy to fly, so you could really stick someone on there who has no experience and they can get by. All right, finally, I think the last project I'm going to talk about is our FAA project for integrated propulsion and control of rotorcraft. So we're looking at aircraft that are using multiple rotors. They could be lift plus cruise, multicopter. So when we look at those types of rotors, there's typically a few ways that the developer of the vehicle might choose to have thrust generated. By far the most common is to change the thrust by changing the RPM. So in this case, you have to speed up this propeller or prop rotor or rotor in order to generate more thrust. So one problem with that is that the larger that your rotor gets, the more inertia it has, which requires a lot more torque to speed up. There's also a lag between when the pilot wants more thrust to you actually get more thrust because you have to speed the rotor up. So a way to avoid that is to govern the RPM at a set RPM and use variable pitch on the blades. So that would be how helicopters work. Helicopters also include cyclic pitch, where they can change the pitch of the blades as it goes around the azimuth. This will create an asymmetric loading on the rotor disc, causing the rotor disc to tilt. It'll also generate, in some cases, if you have a rigid rotor system, a large moment at the hub. So our idea, and what we pitched to the FAA, was to study if we were to use rotors with full helicopter controls on a multicopter, what kind of redundancy does that buy you? What kind of added control power does that buy you? So our one of the questions we ask is, will this allow us to, if we have rotors that fail on a system, as you see on the right, can we keep all the other rotors turning and just cyclically pitch them so that they create a moment to keep the aircraft balanced? So that was kind of our hypothesis, was that yes, this will work. So that's what we went in to investigate. We have a lot of different technical approach elements. The main four that you see in the middle, there's some offshoots, but we do a lot of component and flight tests, which is on the top. You can see a small picture of our two 80-pound quad rotors that we built. I'll show you a better picture of that in a minute. We also had a rotor test stand, which is in the upper left. We also built vehicle math models. So in a similar way, as I've spoken through the presentation, we like to test, and then we build analytical models. We want to validate those models so that we can do more things with them. And so on the left-hand side, you see our vehicle model and simulation analysis, where we can do different things like control requirements analysis, control allocation. And all control allocation is many of these eVTOL companies, they have, or not companies, but just the designs themselves, they have more controls than they need. They're what we say over-actuated. So they have the ability to lose some of those controls and still function in a maybe to a safe landing. But how you move those controls nominally and off nominally requires blending them in a certain way, and that's typically called control allocation. A good example on most aircraft for control allocation is your ailerons. You have two, you only need one to control yourself. So what's the control allocation? Typically, I mean, there can be some differential aileron movement for adverse yaw, but mostly they're just slaved together. One goes up, the other one goes down, but that in itself is an example of control allocation on an aircraft. In the bottom, we have handling qualities, prediction, and assessment. There's many tools available to us that we are using to predict the handling qualities, which, again, it's a prediction, or you can try to set a design specification for that, but only through actual either piloted simulation, which is on the right-hand side, where we can look at our test pilot actually flies the aircraft in the simulation before we go out to test, and then through testing itself do we rate the handling qualities and see how well we come to our prediction. Anytime you have rotating machinery, you get vibration. So that was something that we experienced as well. And to counter that, we tried some different, in this case, you see a boom with a rotor on the end that mimics one of the arms of our quad rotor. And in this case, it's round. We did have one that was square. We had some vibration issues that we actually solved on the square boom, but in moving to this, we started doing some testing on the booms themselves to see what was the level of vibration, what could we do, how did it vary with RPM to try to find out what the resonant frequencies were. So like I said, we do a lot of testing in addition to our analytical work. So these are the two quad rotor test beds. They both weigh about 80 pounds apiece. Pictured here with two-bladed rotors. We've since moved to three-bladed rotors because that significantly improved not only our thrust capability, but also the vibration levels. And this is just a shot of some of our team on a typical test day. In the upper right, we have a test stand that's gimbal, so we can actually mount the vehicle to it. It can't go up, down, or translate in any direction, but it can pitch, roll, and yaw. So we could test different flight control laws. We could tune flight control laws with it sitting on this, with it safely sitting on the stand. In the middle, and you're going to see a video in a minute, you can see the vehicle actually flying with one of the rotors inoperative. So we just turn that rotor off. We're still able to take off. We can keep the flight controlled, and we can even maneuver around and come back for a safe landing, all with one of the rotors turned off. So here's a short video of one of our quad rotors in just a nominal flight. It's being tested. And then in this video, you see one of the rotors turned off, and we're still able to fly around with that rotor inop. You would not, in fact, we've tested this, you cannot do this if you're using RPM control on a quad rotor. If you have more than 4 motors, you know, there's an opportunity for some of those, but to stay in where you have your attitude controlled and not moving with one of the rotors in op was one of the outcomes of our research, and it also talked about some of the control laws that we use. Over here on display, we couldn't bring one of our 80-pound quad rotors with us, so we brought a miniaturized version of that. This weighs about 4.5 pounds. We're still trying to have it be the same power to weight ratio as our 80 pounds, but this aircraft uses the same flight control software. It just gives us more opportunities for testing because we're not limited to where we can fly it. We don't have to, we can go out to an RC field and fly this without some sort of certificate of authorization from the FAA to fly something that's over 55 pounds. Some of the interesting things, since I have a minute, that we can do with this and public domain knowledge, written papers on this, is that for most RPM controlled or collective controlled aircraft, when the aircraft needs to yaw, they will either do differential RPM change or differential collective change, which creates a change in the total torque that's on the vehicle, and it will cause the vehicle to yaw. The bigger that an aircraft gets, the smaller the effect that that has. So yaw performance will degrade, if you, all things being equal, as you scale up the vehicle. So you see a lot of manufacturers and even hobbyists that have big drones, they'll tilt their rotors some, which provides a component of thrust in the yaw direction, and that can significantly improve the yaw performance. So we do not have our rotors tilted. However, we can apply cyclic pitch, which will lean all the rotors discs in the direction of yaw. And so we're able to achieve some of the effects of having tilted rotors just by using cyclic. In fact, it's with that control law that we're able to fly with one of the rotors inoperative. So kind of to summarize, we're engaged in a number of research projects related to urban air mobility and electric vertical takeoff and landing aircraft, alternative propulsion with our hybrid systems, and we have battery development and eVTOL flight simulation. So a number of different projects across the entire ecosystem of UAM. External funding that we get from different companies and government organizations like the FAA really is providing us growth so we can have more students that are funded, that can have their tuition, graduate student tuition paid for and receive a stipend while they do work at our center. And probably most importantly is our students are receiving not only theoretical experience, but they're learning hands-on experience. You know, they're learning how to program inverters. They're learning what it takes to design and build a battery pack, or how to build a hybrid electric power system. And many of our students go on to work for urban air mobility companies. We have someone that went to work for Joby. We have a student that went to work for Skyrise, and there's many others that are out working in the urban air mobility and eVTOL field that came from the Eagle Flight Research Center, and we hope that that continues. So that's all I have for the presentation, right on time. I guess if anybody has any questions, you can come up and be happy to talk with you.